Hi, good evening, and welcome to the inaugural Cambridge AI Social Lecture. My name is Aaron Turner, along with Matthew Burkett over here. I'm one of CAIS's founders. Before I introduce our fabulous speaker for this evening, I'd like to quickly describe the motivation behind tonight's talk. So, in the mid-1960s, Joseph Weizenbaum at MIT developed ELIZA, which was the first ever chatbot. It was an extremely simple program, far less sophisticated than a neural network, but many at the time perceived ELIZA to be far more intelligent than it actually was. And this was later dubbed the ELIZA effect. If we fast forward to November 22 and the release of ChatGPT, that piece of AI technology has probably had more press than anything else I've seen in the last 40 years. Nevertheless, under the hood, it's a large language model. And large language models calculate the statistical relationship between words or tokens in its training corpus. So, just like a dictionary, all the words or tokens are related to each other circularly. But if all the definitions are circular, then where's the meaning? So, like a dictionary, a large language model does not contain any grounded meaning. It's not, the words are not connected with observations or experiences of the actual real world, meaning the actual things that the words are supposed to represent. So as a result of that, large language model based chatbots do not understand either the input prompt that they're given or the output that they generate. It's just a statistical continuation of the input prompt. And without understanding, there can't really be, without any depth of understanding, there can't really be any significant reasoning or cognition. And therefore, just like ELIZA, ChatGPT conveys essentially the illusion of intelligence. It's much less intelligent than it actually appears to be. And all the hype we've seen is basically the ELIZA effect on steroids. Now, ChatGPT and its cousins may nevertheless provide some valuable utility, but in terms of intelligence, reasoning, and cognition, from an AGI perspective, it essentially doesn't have any. Now, if we look to the future, how can we build AIs that actually do have genuine reasoning ability? So it appears that there are three modes of reasoning underlying critical thought and problem solving, and they are induction, deduction, and abduction. Of these, deduction has a roughly 2,500 year history and is the best understood of the three. The art of applying modern systems of deduction is called theorem proving, and the art of automating theorem proving on a computer system is called automated theorem proving, or ATP. Now, automated theorem proving is related to AI in two different ways. First of all, it's a very, very hard problem, which means it's a good application for AI. You could try to build an AI system that performs or facilitates theorem proving. And if you manage to achieve sufficient performance in that regard, then you could actually use automated theorem proving as a component of an AI such that it could actually perform genuine deductive reasoning. I have to point out these are really difficult things to achieve, but these are the possibilities. So tonight's speaker is Professor Lawrence Paulson. Professor Paulson has been a world leader in automated theorem proving for over 40 years. He graduated from the California Institute of Technology in 1977 with a BS in mathematics. He obtained his PhD in computer science from Stanford in 1981. He arrived in Cambridge University in 1983. He was elevated to Professor of Computational Logic in 2002. And in 2022, last year, he became Director of Research at the University of Cambridge Computer Lab. He was elected a Fellow of the ACM in 2008 and a Fellow of the Royal Society in 2017. All of which means we're extremely lucky to have him here. So allow me to introduce live and in colour, the one, the only, the fabulous Professor Lawrence Paulson. Thank you very much.
Okay, so I'm going to try and cover logic, the technology of logic, some of my own particular work, and then some implications for AI in the following hour or so. So first, I guess, history of automation. And before I start, I just want to get a little of the jargon down because it tends to come out and that can be incomprehensible. So if I say propositional logic, that just means Boolean logic. That just means and or not kind of big deal, right? If I say first order logic, that means we have quantifiers, so we can say for all x exists y. You can express things like all men are mortal, that sort of thing. If I say higher order logic, then I can talk about functions directly, so I can say for all functions from natural numbers to natural numbers, there exists assumption. So, and again, so that we can know what we're talking about here, what are you going to talk about when you have put a formal logic into a computer? First, you need to be absolutely specific about the syntax, simply the grammar. What are you allowed to write? What is a well-formed formula? Also, with the syntax, you have to have meaning, you have to have semantics. Now, the funny thing is, the semantics is not actually in the computer, but nevertheless, without semantics, without meaning, the whole thing is totally a sterile exercise. We need automation. That is, we need a way of finding proofs automatically because they take a long time to do one step at a time. Okay, going back to history, I'd like to mention a long overlooked person named Hao Wang, a Chinese-American philosopher who got very interested in formalizing mathematics and built the first reasonable theorem prover. He tested it by proving, well, there's a book called Principia Mathematica published by Russell and Whitehead in which they wrote down an enormous amount of mathematics by hand. He found all the purely logical results there, typed them all in, and managed to prove them all in a very short time and fully automatically. Now, this computer, what is an IBM 704? I don't know how clearly you can see that. That has 6 valves, 4,000 operations a second. So that was a pretty good accomplishment. This was an age. All these pioneers in the 60s were mostly philosophers. I mean, the kind of philosophers who wrote essays. So I mentioned Hao Wang, there's Martin Davis, Hilary Putnam. Certainly they wrote essays. These other guys like Logeman, Loveman, and so on. Again, most of them are philosophers, classicists, people of that sort. Some of them had mathematics degrees. And they built the these were all early things they did that evolved into the stuff we have today. So in particular, see the arrows show what they evolved into. So there are some very powerful techniques called connection methods for proving theorems, superposition, which talks about theorems, including very clever stuff with rewriting expressions, and then the whole Saturn SMT world. Now, these technologies, as we have them now, SAT is dealing with large Boolean problems. When I say large, I mean like maybe 1 million Boolean variables, and again, thousands and thousands of so-called clauses which constrain the Boolean values. Now, although the Boolean world, I remember, is just and or not, so it seems it's trivial, but if you've got a million of them, you can encode an awful lot of stuff, and it does things automatically. And likewise, I'm not sure I want to go through every one of these in detail, but they have a lot of fully automatic technologies that can prove a lot of big things. That's great. So why is there interactive proof at all? What is the point? Well, it's maybe a paradox that you can have a thing that can deal with a million Boolean variables automatically, but it can prove a relatively easy thing like that there are infinitely many prime numbers, or that the square root of 2 is irrational. The arguments that you need to do this somehow are beyond what can be found automatically. But also, the automatic technologies I've shown you are almost entirely either just Boolean logic or first-order logic, and those are really very weak, impoverished formalism. If you want to express mathematics, you need at least some kind of higher order logic. You want to talk about function. You want to talk about sets, and they can't do it. The other point, and especially if you're interested in if you think of a computer science verification project, so you want to verify a processor or some kind of software system, typically you have a lot of specifications, pages and pages and pages of formal specifications that are all part of the thing that you are verifying. Now, when you do that, suddenly this is much, much too big for those automatic things I told you about. And so my little slogan here, that interactive theorem provers should be called specification editors. It's not a joke. It is more like half of your time you are managing this gigantic hierarchy with maybe hundreds of predecessor, what we call theories, that is formal documents containing specifications. And part of what you're doing, you're not only proving theorems, but you're editing these things and developing all these things and managing them. Okay. Then why would we have automation and interaction? And it's simply that they're huge. And we need to use the muscle of a computer. I have a really naff animation coming, so let me give my apologies in advance. I mean, that is like the stupidest thing, right? However, the point I want to make, so like this is a nice laptop. It's got 12 cores. And you might say, oh, you're proving theorems. Now, you can use one of those little MacBook Airs, can't you? No, I can't. I always have, you really need as much muscle power as you can afford, because we are running things in parallel. I can get all 12 cores going to run searches for things. And this is what we're trying to do is hard, and we need the computer to do as much of the work as possible. Okay, so just a little bit about what interactive theorem provers we've got. And we've got two worlds. So there's the world of simple types. I wonder who's heard of dependent types around. I don't know how well known that world is. Okay, no hands are up. So when we say simple types, these are the types like you might see in a normal programming language, like things like int, bool, or functions. With that notion of type, there is a variety of systems shown, like these ones shown here. So if you choose higher order logic, which is a thing that they normally prefer, you get a relatively simple and well understood calculus in which you can still express almost anything you want. So my recent work has been on formalizing professional grade mathematics. And what we have found is that so far everything we try to formalize, we can formalize. So there is nothing that we can see at the moment which is beyond our capabilities. And finally, automation in the simple typed world is relatively straightforward. There is another quite big world, the dependent type world. So here you have types possibly parameterized by values. So a very typical thing is lists of n elements where you have list of n as a type. So the ability to write that sort of thing clearly gives you a more sophisticated system. And the kind of calculi people are looking at are, in a formal sense, in a mathematical sense, much, much stronger than the simply typed calculi in the left column. Often these people pursue some notion of constructive proof, which unfortunately is often not constructive in a meaningful way. So there is a lot of, I think, silliness going on there. But there is a lot of very good work done in the dependent type world, a lot of very exciting work, and a lot of mathematicians prefer these systems. Okay, now as I'm going through an architectural tour of theorem proving, I want to mention a thing that is quite important. I wish I could say it was developed in Cambridge, but it was developed in Edinburgh. And a lot of people have forgotten it. Now, I don't know if you people are systems guys or what, but everyone knows what a kernel is, right? So an operating system kernel is a thing that runs in kernel mode in your processor and is responsible for managing the lowest level tasks of the OS. And if you have a kernel-based OS, the only way something can really go wrong is if it goes wrong in the kernel. So the whole point of that architecture is that no matter how awful the code outside the kernel is, it can't do any real harm, because every time it wants to do anything dangerous, it has to ask the kernel, and the kernel might not let it. Now, we have a very similar architecture for theorem proving, and you might say, why do you care? And the reason is we get very upset when we prove 1 equals 0. So we don't want that to happen. So we have a kernel too. And what's in our kernel is simply a list, or not literally a list, but embodied in the kernel is all the legal logical steps of your particular calculus. And they are put in very literal form. When you want to make a theorem, if you have a thing that says P and I have Q, the conclusion is P and Q. And don't say big deal, there really is such a thing. That's how you form a conjunction. That's in the kernel. So if you have some really super sophisticated theorem proving thing, it will probably be outside the kernel, and whatever clever thing it wants to do, it has to somehow reduce to the rules of the actual calculus and say, yes, P, Q, P and Q, yes, that's okay, out you go. Now, the cool thing is, so we don't have a kernel mode. You know, hardware is giving your kernel its special protection on a computer, your operating system kernel. Here we rely on the type system of a programming language to ensure that the abstract data type in which your logic is sitting is protected from any manipulations from outside. Now, the point of a kernel architecture, and it's the same for us as for the OS people, is, of course, it improves reliability. It does make things, and I think for an OS that they say it's less efficient that way, and I suppose the same can be said about a theorem prover. The necessity of pushing everything through the kernel can make things trickier to code and less efficient, but we put a very high premium on correctness, so we put up with this. So lots of systems, I mean, I'm not sure how familiar you are with all these systems. Most of them use some variant of this approach. Now, just to give you an idea of what you would find in any interactive theorem prover, aka proof assistant, a lot of this stuff is fairly routine. So you need a specification language for saying I'd have a type that does this. I want to define a function. This is the thing I want to prove. You have the ability, you have, if you like, a simple functional programming language, so to speak, so that you can define recursive things. And also you need a language of the actual proofs. Above that, you need a way of managing. I mentioned you had this big hierarchy or big directed graph of all your specifications, so you need something for that. Of course, you need a decent interface to all of that. Lots and lots of other stuff. So now I get to talk about my own personal work. Oh, it's not my, this is a big collective thing now, but I had something to do with this. So Isabelle Hall is one of these interactive theorem provers. It had some, now it's interesting, what this thing I call classical proof search is actually a development of how Wang's work. So his original ideas are still there. We also have counterexample finding, because you're often wrong. I'll say more on that. And we have the sledgehammer, which is kind of like the bulldozer, right? It's where we want to use a lot of computer power. And we also have a nice language of writing the proofs themselves. So I'll show you all these things later. And the cool thing that I can't demonstrate, but which is there, is that it is very good. It's actually highly parallel and can use up to 12 cores effectively, even in processing a single document. Now, our language, I mentioned higher order logic already, but just to say a little more. So you can see it as first order logic, that is Booleans, quantifiers, types and functions and sets. The types are polymorphic, which means that kind of like, I guess some modern programming languages have forms of polymorphism now. So the ability to have list without caring what the type of the element of the list is, that you can plug in natural number, Boolean, integer, real, and it will all work. It's very easy to model a whole variety of things in higher order logic, whether it's hardware, software specifications, crypto protocols, mathematics, all of those go in. And there's a very nice slogan due to my colleague Tobias Nipko that it's like functional programming with logic added in. Now I want to go through some of my points in a bit more detail, the things I advertised earlier. So I mentioned this how Wang-like classical search. And I have a couple examples of things that can be proved. Now, this is a funny thing. I mentioned at the very beginning of my talk, the automation of really powerful automatic theorem provers. So if you look at this formula here, I imagine if you stare at that for a while, you'll scratch your head and probably scratch your head a bit more and finally say, is that really a theorem? And I don't pretend to understand it any more than you do. And the funny thing is, so this is like a gap between the really automatic ones would look at that and just laugh, right? And this is not even a test problem. That's how trivial it is. And yet when you're at the level of the sort of technology where you're talking about here, this is actually quite a tough problem. So we have the two worlds of the automatic worlds and the interactive world are really very part of our goal is to try and bring them together. Now, the other thing you see, that other formula probably looks quite intuitive and obvious because it's just a distributive law for unions, but it's also a kind of thing that can be quite tricky to prove if you don't have the right automation. So again, I'm going through a list of stuff we have in Isabelle. I think because it is useful and interesting. So as I said, many of the things you might want to prove are not actually true. And that's awfully frustrating, but they're not true because you typically are working with complicated things. You overlooked a necessary condition. Maybe you stated something incorrectly. Maybe you didn't quite understand your problem. So you write down a thing, and if before we had these tools, what you would do is work and work and work and work and get angry and hit the wall and so on and go home and then say, oh, fuck. And all that is very unfortunate. Whereas now, and if you're lucky, it will just say, hey, it's not true. Look at this. And it can actually give you, if you're lucky, it's not always available, but in a great many cases, one or the other of these things can walk through your formula and say, nope, here is a counterexample. A very handy thing to have. Now, what is sledgehammer? Again, I mixed my metaphor because I had the bulldozer, now I'm choosing a sledgehammer, whatever. This is where we integrate the interactive world, which I typically work in, and the world of those super powerful automatic systems that I mentioned in the first part of the talk. So this was a project I led nearly 20 years ago. The task is to somehow take the problem you're working on in your interactive prover, package it up in a form that makes sense to these other provers, which have different logics and different everything, so that they can run and work their magic and give you something back. And then, because we don't trust these systems, because there's mountains of code written in C++, which we certainly don't believe is a way you can write anything that's trustworthy. So we have to extract from their claimed proof something that we can use and generate a proof ourselves. And the point is, from the user's point of view, this has to be as easy as clicking their mouse once. So, and that is a cool thing. And so we really have this, and I can go through, in fact, I was doing this as a kind of boredom activity, go through old proofs that were done without this, look at the proof, put the mouse in the right place, click. Very, very often it will replace a proof of 5 or 10 lines with a single call to something that will just prove the whole thing. And this really transforms how you work and everything. So, just continuing, again, I'm going through what we have in Isabelle. We have a big library. So lots of people out there have been proving theorems. So what is that graph? That is the number of entries in the archive of formal proofs, which, what is that? Going up to 800, I think. And you can see it's maybe even superlinear. So, and of course, these libraries can be used and imported. Some of them are very popular and are built upon to make new entries. Many others lead nowhere, but whatever. Just to wind up the Isabelle part, lots of different projects have been done by people. So in computer science, the thing, if I can talk about myself again, I did a lot of work on verifying crypto protocols, which some people thought was very cool, but also some work on Java semantics. There's a whole book, I think, of proofs of verification of algorithms, including, I think, the complexity of algorithms. Tons and tons of advanced mathematics has been formalized, and some quite advanced results in logic. So the Cook-Levin theorem is apparently quite a big deal. And yes, if I can talk about myself again, the formalization of Gödel's two incompleteness theorems is something I did about 10 years ago. As for more industrial applications, I could only find this one, but it is quite a big deal. So this is a verified OS kernel. This is a commercial product. This was completely verified down to what? I'm not sure. But they have a full functional specification. So when I say verification here, this is not about saying that there are no overflows or no legal memory references. This is saying that it does exactly all the things it is advertised to do. And I know this has been deployed in some security applications, so I think this is meant to provide you with a security kernel or something of that sort. Okay, and this is just there to impress you. I think there was a time when I would kind of walk through those one at a time, but this would be very tedious. But there's been an awful lot of different phases in the development of Isabelle, and you can see that most of those represent a lot of work. But I think I've probably said enough about Isabelle, and people would probably like me to talk about the kind of things that this is meant to be about. So what about intelligence? So as Aaron already said, there are deduction, induction, and abduction. Well, I'm not going to mention abduction at all. Now, let me just mention, and I'm not sure how familiar even induction. So when I say induction, of course, I am not meaning mathematical induction. So what is meant by induction is the scientific process of I observe, let's say, the stars moving in a certain pattern night after night. I see that there's these other things which are moving in a different way, and I start to deduce certain laws that they seem to obey, and over time come up with maybe some theory as to how they're going to move in the future. That's called induction, or philosophical induction, or inductive reasoning. That's the basis of all science. So you take a thing, you observe it, and the problem is you're never sure whether you're right. You're never sure whether there'll be an exception to the pattern that you thought you saw. The other thing about inductive logic, so I think chickens are good at this, so I'll show you in a moment. But in fact, even plants, you know how plants grow towards the light? The plant is, if you like, inductively reasoning that there was light here yesterday, there will be light here today. On the other hand, deductive logic is when you have some axioms of some sort and you follow some inference rules and you result in some conclusions. And this is perfect. So if you got a thing that's perfect and a thing that's imperfect, why would you use the thing that's perfect? Well, there's a kind of catch-22. The perfect world of deductive logic has nothing to do with the world we actually live in. Isn't that annoying? So the perfect world of mathematical induction is for the ideal Platonic world of mathematical things there in our minds, or maybe in some Platonic universe if you want to prefer it that way, but it's not going to put pizza on the table. Now, what's interesting is there is a way of mediating between the two. So in our inductive logic, we make our observations, we make a theory of trying to predict things. If our theory is mathematical, then we are using mathematics to make predictions about the world, and now we can do logical deductions about our mathematical model in the hope of making predictions about the world. So if you, for example, send a probe to Mars, you're using just Newtonian mechanics. That is a mathematical model of how the universe works, and it seems to work pretty well. So following this mathematical model, the probe does indeed get to Mars. So you could argue that we are using deductive logic to reason about the real world. But we're reasoning about our model of the world, and we're hoping our model is accurate. But the world always has the right to behave however it wishes to. If Mars suddenly moved a light year away just like that, and tell you, well, that was interesting. And the scientists would have a big job trying to figure out what on earth happened. Anyway, let me continue with my slides. So this is chickens reasoning inductively. You see, the nice lady comes and feeds them, and every day she comes, and every day they rush up to her, and she feeds them. Isn't that nice? But you see, with inductive reasoning, and this is the only reasoning we have really to navigate our world, to get our pizza or whatever, to drive home from work, or like here when I thought I would come here in good time, so I'll have a taxi and have a half an hour just to come out to the science park, and it nearly took an hour. And in fact, to do that, the driver went off Milton Road and went driving on some crazy route and said, I'll go and I'll get via Arbery Road instead because we'll never get there. Anyway, so inductive reasoning is what we have reasoning about our real world. As for deductive reasoning, it's something like this. You have a Sudoku. You have certain rules for what it means to be a solution to a Sudoku. There is no ambiguity about what is a correct solution. This is not a thing a chicken can do. And we are not good at it either. Now, there was an idea, I guess about 100 years ago, that human intelligence consisted of the ability to manipulate symbols. And I guess the early IQ tests were very symbolic, and early AI was also very heavily symbolic. These are things that people find difficult And a lot of the things that people do, which is a sign of great intelligence, like being able to write a novel or something like that, is not symbolic at all. So linguistic capability, that is the ability to write, as I said, a novel, a poem, something like that, does not appear to be symbolic in the sense of a Sudoku like this. Now, as a logic problem, this is hard for us, but it's trivial. So I mentioned there's an automatic technology called a SAT solver. You can encode the constraints of a Sudoku as a Boolean problem in a very boring way. It would be an enormous, well, not enormous. 1,000 or so constraints is actually not a big problem. Give it to a SAT solver and it will solve your Sudoku in a couple of milliseconds. So it's a trivial logic problem. So remember, we find this hard, but logically, this is trivial, even in the empirical sense of how long does it take to solve. Milliseconds, as I said, not by special computer code, but by a general logic solver. Now, some of our AI friends have what they used to call the artificial intelligentsia. So John McCarthy, who's very famous as the inventor of the Lisp language, garbage collection, the whole idea perhaps of artificial intelligence, he's very tied up in all of those things. Now, at some point, the AI world became aware of what's called the problem of common sense reasoning. So as early as the early 60s, they already had a program that could solve calculus problems as well as a first-year MIT student. And they got a bit carried away, and one of them, Marvin Minsky, who was the scientific advisor for the film 2001, and he probably really told Stanley Kubrick, yes, you can have a thing like HAL 9000 by 2001, because already in 1963 they could beat MIT students. Okay, it's 2023 and we haven't got a HAL 9000. And what they hadn't understood was that although they could beat an MIT student at solving calculus problems, they couldn't beat a 4-year-old at understanding a program about a story, a children's story about a couple of rabbits. So, and this was the paradox of common sense reasoning, that the hard things were easy and the easy things seemed to be impossible. So common sense reasoning means a lot of things, but it's kind of like, so if Jack is a bird, well, Jack can fly. But if they say, oh, well, Jack is a penguin, oh, okay, Jack can't fly. That's a kind of common sense reasoning. And what McCarthy wanted to do is say, well, he wants this thing called non-monotonic logic. And the idea is, in normal logic, the more you know, the more you can prove. So if I say, okay, oh, plus x is greater than 0, you know more. Now that you know that x is greater than 0, you know more than you knew before, and you can prove more than you did before. Whereas, with non-monotonic reasoning, they say, Jack is a penguin. Things that you had thought you'd known, like that Jack can fly, suddenly go away. What's wrong with that? What's wrong is that he's trying to do inductive reasoning through a deductive approach, that you could somehow make a list of formal things and arrive at what is effectively inductive reasoning. So this is just not a thing that could work. I mean, people are still writing papers on this. And of course, they're not stupid. So of course, they're trying approaches that could do something. But to my mind, this is just cannot be the right way. Kowalski also did an awful lot of things connected with, for example, I think he was looking at legal codes or its legal specifications and contracts written in English, trying to convert them into logic and make deductions about them. And that's actually quite an interesting thing, because if you have a legal contract, it is giving you very specific constraints that are required to be satisfied. They can be seen as a problem of logical deduction. And the time may come when these things are actually expressed in some kind of formal and some kind of proper logical formalism. But this is not a thing that people seem to be ready for yet. Now, As Aaron has already said, we can see automated theorem proving as either an application of AI or an engine of AI, but I'm not, yeah. As I said, I don't think even very smart people are using deductive reasoning very often. Even when they are doing whether they're, let's say, you're Warren Buffett and you're making billions by predicting which companies are going to thrive and which ones are going to fail. I would guess he is not proving any theorems. He's looking over various figures, and he is probably getting a figure. I mean, he is making certain calculations for sure, and that is deductive. And at some point, he's saying that doesn't look good, and he's saying down with that one, and so on. Anyway, I should continue. So we're interested in AI. So can AI prove theorems for us? Now, I want to say something about the way formal proofs are done on interactive theorem provers. So there's a very well-known theorem prover called Hall-Light. And this is a proof of the mean value theorem, which is a theorem of calculus. Sorry, that's not all of the proof. There is a bit more. And there's some more. Isn't that beautiful? It works, but it's not very nice. So, of course, I'm here to say how great Isabelle Hall is. So that is the same proof. Now, of course, you don't know this language, but I hope you can see that there are things there. So there are some formulas, some logical assertions that one can read. So we're assuming A is less than B, whatever they are. There's a thing called phi, which might be a function, and it's continuous between A and B, and so on. And inside there, you can see certain claims that are being made, and under certain assumptions, we can show that FA equals FB, and so on. So if you have a thing like that, you have a much better chance of understanding what's happening simply by looking at the proof itself. So we have an expression of the reasoning underlying the proof. Whereas what you had on the previous slide was literally a computer program which, when run, would cause the theorem to emerge from the kernel. That is the difference. So these are nice to have, partly for their legibility, and that's partly because, especially if I'm selling this technology to mathematicians, they never trust us. And it's much better if they can look at the actual proof and say, oh yeah, okay, yeah, that looks right. This might help us to reuse things. It helps us maintain our code. And I wanted to say, actually, if I had remembered, so if you remember that photograph of the bulldozer, in the background there's this gigantic hole in the ground. Now, just as there are some people there who avoid automation because they're afraid the automation will go wrong, and that is a bit like digging that entire hole in the ground just with a spade. Now, we don't want to do that. But I meant to be talking about AI, so let's see, what does this have to do with machine learning? If you got a structured proof, you've got a lot of local contexts, and then suddenly, instead of trying to prove the whole theorem at once, and I know a lot of early ML work on theorem proving is trying to prove the whole theorem at once. This will fail because most theorems are much too difficult to just prove right off the bat. But if you can just go from, here I am, I've proved this much, I've done this part of my development, can you give me the next step, please? That's more plausible. And maybe you can see some patterns from some idioms from other proofs that are similar. And what is this starting to sound like? Well, it's starting to sound like a language model, isn't it? And these things already exist. There's a lot of some of these designed, for example, to take an English description of a problem, like, you know, show that if you've got two normal subgroups of a group G, then blah, 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 and turn them into a completely formal specification, or to transform a proof of a statement into a completely formal proof. Or to try and generate a proof, so if you can just ask it, write me a formal proof of a certain thing. Now, as we know, ChatGPT is often wrong, and it can be very amusing. So I asked it about myself, and it gave me all kinds of awards and all kinds of activities that I'd never actually done. But it thought, well, some people would have this or that prize or this or that thing, and oh, yeah, that's not bad. But the thing is, these formal texts are checkable. We already have the software to check a specification and to check a proof, try to run the proof, and if it runs in proof or theorem, we're happy. And of course, you can run a language model over and over again. It gives you things one after another, and only one of them needs to be good. So there's already some work I've seen where people are taking a couple of these language models to translate a problem into the formal language, and then to somehow give you the skeleton of a proof, not a complete proof, but merely the skeleton of a proof. And then we use our other automation to flesh out this skeleton. And if all those things succeed, the theorem has been proved. So this is a thing we can do. Now we have our 4 million lines. That's maybe not a lot by the standards of a language model, but at least it's not nothing either. So I think there is some hope for using the language models in the future. And so our future, I asked Stable Diffusion to give me a robot proving theorems. So it gave me that. It also gave me this. And that's all I have. So thank you very much. Someone must have a question. Yes, I see someone there.
I was just curious about how these engines deal with infinite series, like proofs about infinite series.
Okay, there's often an idea that somehow because a computer is finite, they can't talk about infinite things. We're not trying to represent the whole of a thing in the computer. So a computer is working axiomatically, exactly, in fact, like mathematicians do. So there was a time, let's say up to the first half of the 19th century, when a lot of mathematics was intuitive, and you couldn't really exactly say what a proof by, say, Euler really meant, because there were some intuitive leaps, a lot of uses of infinitesimals that didn't quite seem sound, and so on. So there has been a process from about a century, ending in around, let's say, by the 30s, the 40s of the 20th century, that we had mathematics on an axiomatic basis, whereas a theorem about infinite series, for example, had a completely rigorous meaning in terms of epsilons and deltas or whatever, or now, and in fact, with non-standard analysis, we could even deal with them using infinitesimals in a sound way. And we are using exactly the same formal logical principles that a mathematician would use, and they can be written down in a computer. Does that make sense?
When you mentioned the almost language ChatGPT style theorem proven, it almost sounds like you were suggesting just a random brute force approach of churn out a potential theorem, test it, see if it works. So maybe more targeted than monkeys on a typewriter, but maybe something like 10-year-olds on a typewriter trying to churn out a story. Is there more to it than that?
Yes, to brute force or not to brute force. It all depends on how you get the answer out. I think when I was younger, I always thought, oh, how ugly. I mean, you're doing a case split over all the variables, and my colleague said, well, it proves the theorem. So this is very early work. So I said this brute force approach is very early work. If it can be beaten, then that's fine. But if we look at the history of computer chess, you had on the one hand the things that did gigantic searches, and on the other hand the things that tried to think like a chess master. And on the whole, they were beaten by the ones that did gigantic searches. So brute force often seems to win, and ultimately what I care about is proving the theorem. There was another question.
I was going to ask about, you showed there was what looked like a hyperlinear growth in the number of theorems that we have. And what's the main driver behind that? Is it increased technology or more people?
Oh, that's just people. That's only a slight upward curve, but it just as people. I think that technology has improved to make it easier to do things. So it's very nice that you can have 12 cores, and we have the things that we can use those cores on to, like this thing called Sledgehammer is going to run typically 5 automatic theorem provers simultaneously. And only one of them needs to come up with a proof. Again, this is a very brute force approach. We take the one that we find is the shortest or most elegant or whatever and stick it in. So as things get easier for people, as they get better computers to do them with, and as the word gets around that you can do this and it might be fun, then yeah, you get more people.
Oh, so it's more people coming into
That as well, yes, for sure.
So the brain seems to be a very inductive instrument. So when the brain processing the theorem proof, what's really behind it? Is the stuff really behind it still language? Because for example, if you ask me to prove a English theorem, I'm still gonna think in Chinese because that's my language.
Yeah.
So what's really behind it?
I don't know a lot about brains at all. But I do think, as I said, that deductive reasoning is not very natural for us. We have to work very hard to do it. And I think that there's a lot of intelligent behavior that does not involve deduction at all. I imagine when an artist is working, they are not proving theorems, they are creating a thing. They know what's going to work and what's not going to work. This should be there, that shouldn't be there. And it's not an exact calculation. It's a thing they know, and that is intelligent behavior. And I'm sorry, I'm not a psychologist, so I cannot talk with any authority on this sort of thing.
So basically behind everything is still some sort of language model, because our brain is sort of built that way.
I wouldn't say that. I would say a language model is trying to copy what the brain does. There's no reason to think the brain is a large language model in any way. I mean, it's remarkable what those things can do. As I said, I'm not a psychologist, but I would be surprised if there was much similarity. It's certainly true. I mean, people who are suffering from dementia are still able to talk in coherent sentences often. So there is something that is still there. And you might say this is something like language model behavior, that they know what word comes after what other word, even though if they have completely forgotten everything. Again, this is something that one should really ask a specialist, which I'm not.
So when you create these rules to prove your theorems, that's very formal, and the communication with the software is very formal.
Mm-hmm.
My communication with the chatbot is very informal. How can you bridge these two technologies?
I'm not really an expert on machine learning either. If you mean how do they make a language model that goes from an informal mathematical problem to a formal one, I have no idea, but I've seen them. I mean, I've seen them in operation, so I know it can be done. It's not perfect. I'm not sure anyone quite knows how these things do what they do. And it is, again, the fact that they're not perfect says, oh, they don't do it very well all the time. And indeed, a lot of English language descriptions are not very clear and precise anyway. Someone in the back here.
At your endpoint, where you're kind of saying you're training the language model, you've got your 4 million lines of proof, are you indicating that this might be able to discover new proofs if it kind of understands and is reinforcement trained by your kind of checker? Could it find new proofs?
Well, I would say two things. First, I think genius in mathematics is not about proving things, it's actually knowing what to define. So it's all very well to prove theorems about prime numbers, but observing that the notion of being a prime number is important is actually the first creative step. So that's one thing I would say. But as for proving new theorems, that's certainly not my own particular push. And I've never believed in AI as replacing human beings. I know that a lot of people do want to do that. I've always thought of assisting human beings. And that with your 4 million lines, you will perhaps be in a situation in your proof where a very similar situation arose in some other guy's proof, and the thing that helped them in that other proof was to do a certain thing, and that the language model could recognize this and suggest that you do that same thing at that particular moment.
Is it fair to say that these language models generally can make very interesting suggestions, but you always need something underneath which checks it out? And that seems to be exactly what you've got there. Your real theorem prover down at the bottom is trying it out.
Well, indeed, the idea that people they're using ChatGPT to generate stuff for them and then presumably sending it off to other people or using it in essays or something like that, I find kind of astonishing, because if you say, unless it's thoroughly checked, what is the point? And then if you're going to thoroughly check it, why not just write your own? Because it's funny, if you actually read the text that comes out of ChatGPT, it's very, very generic stuff, right? I mean, it could be kind of cute if you can ask it to write in the style of Jane Austen. Actually, it can, and that is really quite cute, or H.P. Lovecraft or something like that. But normally, what you get is very generic and very bland, and something that you could probably do better yourself. So I don't really see the appeal of people doing this. So as you say, because you can, unless you have an automatic way of checking what the output is, it's not clear what it's good for. Yes?
You were saying earlier that you could break up a problem into lots of pieces and check the pieces.
Yes, sometimes.
Does that imply then, if there was some kind of AI suggesting a big thing, that you could break up the parts and then give it a fitness score?
Clearly, the way typically that you tackle a large problem is to try and break it down. So that is certainly a way one works. And yes, if you can have some AI tool that will solve some of those pieces for you, that's good for two reasons. One, it's simply reducing the amount of work you have to do, but also the pieces it's solving for you are probably the boring ones, which make you wish you had a different job. Whereas if you could give it your big problem and the thing magically said, this is what you have to solve, one thing, and it's tricky, you're like, okay, now I've got something interesting to think about.
Can you give any examples of, are there people using these tools in sort of the great unsolved mathematical problems?
I think at the moment, probably very few or nobody is using any of these tools immediately to do mathematics research. I think we would like to get to this point. But even if we did get to this point, it would not be for the tool to solve the problems for them. It's more in mathematics, what we're looking at the moment is simply the checking. So you have a proof, in mathematics these days is even very expert acclaimed mathematicians worry about the correctness of the work because of its complexity. So it is merely to have an assurance of correctness that there is a move to try and adopt these technologies. There was some very recent work when there's a Fields medalist named Peter Schultz, and a result of his that he was uncertain about, he put out a challenge to the world, and a bunch of people proved it in a system called Lean. So they managed to check all his things, and that was impressive because this was a brand new result by a Fields medalist that had thoroughly checked and certified in that way. I guess you want to wind up and bring out the pizza.
So, excellent. Please join me in thanking Professor Paulson for that entertaining talk. Finally, yes, the moment we've all been waiting for, pizza time.